Hey, welcome back to Geology 12, and we're going to wrap up the oceanography part here. When we look at ocean circulation, we're looking at, remember, we're talking about surface currents and thermohaline currents, and I've already talked about their percentages. So we're going to focus on both of these, but first let's look at the surface currents. And so the primary forces, obviously wind blowing over the surface of the water, density differences in the water layers, and then secondary forces that may affect the circulation are Coriolis, friction, and then the shape of ocean basins. So an ocean current is really a discrete flowing mass of water. So it is transporting water. Unlike waves, which are energy, a current is actually moving water. So what we find for the surface currents, they're driven by wind, and the surface water often moves in a circular pattern called a gyre, right? So you'll see that in the northern hemisphere, the gyres are moving clockwise, right? And the southern hemisphere, they're counterclockwise. And again, that's due to Coriolis force, that secondary force. So gyre is a circular transport of water in an ocean basin. So you'll find that there's 5 major gyres. There's a North Atlantic, South Atlantic, then we'll see the North Pacific and the South Pacific, and that's 4. And the last one is the Indian Ocean Basin. The Indian Ocean Basin would be the 5th one. So that kind of shows these here. Here I talk about, here it says 6, because the 6th one, it doesn't really go around an ocean basin. It kind of just goes around south, the southern, the Antarctica. It goes around Antarctica. That's called the west wind drift, the Antarctic circumpolar current down here. It's actually a pretty strong current, one of the strongest we have. But it's not really in an ocean basin like the South Pacific and the North Pacific up here. But know about this. And we call them geostrophic. There's a little bit more detail to it because the way their shape and what's driving their direction, Coriolis force is one, but also there's gravity and pressure. But for now, let's just, we'll just identify the 5 geostrophic gyres in the ocean basins, and then we have this extra west wind drift down here in the southern hemisphere. So when we look at these currents in these gyres, right, we're going to divide them into these western boundary currents and eastern boundary currents. So the western boundary currents are warm. It's warm water moving from near the equator to higher latitudes. For example, you've heard of the EAC, the East Australian Current, from the Finding Nemo movies, right? So this EAC it goes from the equator south, and that would be in the South Pacific current. So here's our EAC, right? Moving, it's a pretty fast, narrow, warm water current, bringing equatorial warm waters down to higher latitudes in the southern hemisphere, right? So it's keeping it warm over here in Australia and off of New Zealand there. Now, in the northern hemisphere, we have the Gulf Stream in the North Atlantic, the Kuroshio current, there's no N in there, current in the North Pacific, Brazil current in the South Atlantic, the Agulhas current in the Indian Ocean, and then we talked about the EAC. So know these currents. You should know the western boundary. They're warm, they're narrow, they're deep, they're fast, and they're really moving those warm waters to higher latitudes. So here's a kind of a satellite thermal image of the Gulf Stream, and it's moving up here past New York and going up here into the North Atlantic Ocean. And it's really bringing quite a large volume of warm waters up into basically the sea between Greenland and actually between Iceland and Europe, England. And so what that allows, so it really warms the ocean up. So when the cold air blowing off of Greenland goes over the North Atlantic, it actually warms up. So when it gets to Europe, that air is warm. If it wasn't for this Gulf Stream, these waters would be cold, and then that air would just stay cold, and Europe would freeze, right? So really important for the climate. In fact, your textbook talks quite a bit about climate in Europe and due to this ocean circulation. The other thing your book mentions is that it moves 100 times more energy than the world's demand. In other words, it's a lot of heat energy that's being transported along this Gulf Stream here. The other type of currents that we have are the thermohaline circulation. These are the ones due to density, where we get the cold water sinking, and then spreading along the ocean basin, then rising and then mixing, right? That would be our thermohaline currents, right? And so here we can see that in Antarctica we have the coldest waters. In fact, it's called the Antarctic bottom waters down there. The coldest because we have a big glacier down there. We don't have a continent in the northern hemisphere, but we still get sea ice formation. In fact, that's one thing I wanted to look at is this idea of sea ice formation. So when you think about sea ice, right? One thing about ice, about salt, salinity, right? Salt lowers the freezing point of water. So instead of freezing at 0 degrees, it will freeze at like negative, I think it's 1.98 degrees centigrade, which is essentially negative 2 degrees centigrade, right? So that's below, because remember, water should freeze at 0. So when sea ice forms, the water, the seawater around the sea ice is super cold, right? It's colder than freezing, right? It's at negative 1.98 degrees centigrade. But not only that is that no salts go into ice. There's no place for salt compounds, ionic compounds to go into the crystal of ice. So ice is fresh. There's no so now the waters around the ice are hyper saline. In other words, they're very salty. They're saltier than normal salinity. Remember, the ocean on average is about maybe 33 to 35 parts per thousand. So here you can see like 39 to 40 parts per thousand, right? And so in other words, the water is super cold, which makes it more dense, and super salty, which makes it more dense. So this combination of cold waters and salty waters really makes the waters after sea ice formation drop like a rock. So you get these density currents that start coming down here. Those are the thermohaline currents that I mentioned. And that's in fact, they call it Earth's conveyor belt, where you're turning over the ocean, right? You're mixing the ocean. And it's important because we want to get oxygen down to these deeper waters, right? We want to be able to get, because a lot of organisms live down in the deep ocean, and we want to get these cold and salty waters sinking, right? Moving along the deep ocean floor here. And then as they warm up, we get the shallow waters up here. So there's a big ocean circulation pattern that really connects the entire ocean basin, this thermohaline circulation. So the next concept I want to talk about is this idea of upwelling and downwelling. So upwelling is upward motion of water. This motion brings cold, nutrient-rich waters to the surface. So in other words, areas of upwelling are areas where you're going to see high productivity, and oceanographers use that word to refer to the amount of organic carbon being produced. So lots of plankton, phytoplankton, blooming, which means there's lots of food for other animals to come in there. So it's really a really important area for rich fisheries, where you're going to catch fish, and lots of organisms there, productive. Whereas downwelling is obviously the opposite, where we're going to push surface waters down to the deeper parts of the ocean. And the key thing there is we're going to send oxygen down there, dissolved gases, because oxygen is very important. Again, we're going to send some dissolved gases down to the deeper waters. And so here's a little cartoon showing the northern hemisphere. And so now there's this idea of the Coriolis force. Remember, and this idea of Ekman transport. So I actually made a little cartoon over here of what this Ekman transport is all about. So the idea of this, this Ekman transport, first we talk about this thing called the Ekman spiral. So remember, Coriolis force, remember we're going to be in the northern hemisphere, north of the equator, and the wind direction is blowing. So that means the objects in the northern hemisphere are going to be deflected to the right, right? Remember, they're going clockwise direction, their deflection. So as the wind blows across the water, the first layer of the water kind of starts blowing in that same direction, starts moving in that same direction. But then there's the layer beneath this layer starts feeling that push, and it starts moving a little bit to the right because of Coriolis force, right? And then eventually the layer before that moves even more to the right of that super adjacent layer, the layer above. And then the layer below that moves more to the right. Eventually you get kind of the spiraling effect, right? That's what they call the Ekman spiral. And it's really due to friction between each of these layers of water and the Coriolis force. So obviously if you were in the southern hemisphere, it would be to the left, right? But here we're in the northern hemisphere, so we're looking at the right. But the net effect of this, of Ekman transport, is that the surface waters will move 90 degrees to the left or right from the wind direction. So obviously left in the southern hemisphere, right in the northern hemisphere. And that's what this diagram is showing here. It's showing that in the northern hemisphere, as the waters are moving, the wind, that is blowing here from, it's coming from the north, it's blowing from the south. That means the surface waters have to move away or towards the right. See, it's 90 degrees, which means deeper waters come up and replace it. So that's what we call upwelling. And then here, the wind is coming from the south, blowing towards the north. And so now Ekman transport tells us it's going to be 90 degrees to the right because we're in the northern hemisphere. And so that's going to pile waters up here, make downwelling occur here. So we get this Ekman transport, which really leads to areas of upwelling or downwelling. And your book talks about those as well. And then finally, there is a region along the equator where we see equatorial upwelling. And I talked a little bit about the meteorological equator in my last video. I called it the ITCZ, the Intertropical Convergence Zone. And note that that meteorological equator does not coincide with the geographic equator. The meteorological equator can fluctuate depending on the season. And in this case, it's north of the equator. So, but remember, if you're north of the equator, objects tend to move to the right because of Coriolis force. In the southern hemisphere, objects tend to move toward the south, or toward the left, that is. So in this case, we have the trade winds, right? Remember, the trade winds are in the Hadley cells there. And since the meteorological equator is north of the geographic equator, these southern trade winds are going to cross the equator and still keep blowing into the northern hemisphere. So that means as the wind crosses the equator here to the north of the equator, there's going to be deflection to the right. But anything south of the equator, deflections toward the left. So basically you see these waters kind of like part. They move away from this equatorial region, which means that deeper waters come up to replace them. So that's what we call equatorial upwelling. And you can see that in satellite pictures. So you can see this is showing, cold waters. So colder, deeper waters moving up along the equator. So Quito, Ecuador is right in here. So that's about the equator right in there. So that's a good example of equatorial upwelling. And then obviously it's going to be warmer farther along there. So this is showing that deeper waters are moving toward the surface. All right, so it looks like I covered everything there. I'll see you guys in class on Monday.